Yeah, good afternoon. So everyone, please go to mute mode. So let me so just a moment. Okay. So let me first share today's lecture note.
This call is now being recorded.
So I hope it is visible to all.
Yes, sir.
Yes, sir.
Okay. So in the last class, we did study extensively about diffraction. In fact, the elementary ideas behind diffraction, and then we concluded that there are two different types of diffraction. One is Fresnel, and the second one is Fraunhofer. And then we also saw that single slit diffraction, which is Fraunhofer class of diffraction, is easier to achieve and also therefore easier to study. So in today's lecture, we'll be discussing the theory behind diffraction through single slit diffraction experiment. So like Newton's ring experiment, this is also an experiment, and here we have experimental setup. So we have point source. We have a point source, namely S, and then the length L1, and then we have a slit. Slit means basically we have a we have obstacle with very narrow hole, okay. So then we can call a slit, and then we have the second lens N2, which has focal length F2, and we have screen namely AB. So whatever the notations or symbols I have been using to represent this schematic diagram, so they have been mentioned clearly, otherwise they won't make any sense. And as we have seen yesterday lecture, that because of the length L1, which is kept at at distance F1 from the source S, so therefore this end we will generate parallel beams of light, and therefore we have a plane wavefront. Okay, and you can see these red dots. They are basically the point sources present over the wavefront. Okay, and then you might make an argument where these point sources come from. And as I said last lecture, these point sources on the wavefront is due to the Huygens principle. So a wavefront comprises large number of point sources. Like this, in order to understand Huygens principle, let's consider a point source. So it says that at a distance, at a time t, the light will travel at distance r radially, because this is a point source. And what would be the distance c, which is the velocity of light multiplied with the time t. So therefore we have fast wavefront, this one, and as the theory or the principle says that the fast wavefront should have very large number of point sources, as I represent by solid dot blue dots. And so this blue dots will also radiate light in all direction, and again at a time, let's say t prime, then it will travel radially outward, and we have then again draw circles or sphere in 3 dimension, as I have shown this cyan color. Okay, and then only that travel forward direction we have wavefront, that travel backward direction we don't have wavefront. So therefore when you draw the tangent over this these small circles represented by cyan color, and if we join them, then we'll get the second wavefront. Okay, and then we have second wavefront, again second wavefront has many number of point sources. Again, you can repeat the same procedure, and then you can get third wavefront, fourth wavefront, and so on. And this way, the light wave travel forward direction. Right. So this is basically the Huygens principle. So we have plane wavefront, and then as for Huygens principle, it must have very large number of point sources. Okay, so now this is schematic diagram, right? We explain, right? Actually, this slit is very small compared than the dimension of the length, L1. So now what will so here the B is the width of the slit. Okay, so B is the width of the slit, and so therefore what will happen? The light beam only can pass through this slit. Okay, and then rest beam they won't able to pass through this slit. And since hello, am I audible?
Yes,
Yes,
sir.
sir. Yes.
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
okay, please go to mute mode. So so now we have point sources as I represent by this solid blue dot circle. You can say the circles, right? And as per the Huygens principle, so it will have fast wavefront like this. That means they can travel in all directions, right? So for example, this it can travel this direction, this direction, this direction, this direction, and eventually one beam will be this direction. So all the point sources will have a beam which travel parallelly with respect to each other. So other person, and you can see, right? So this travel straight path, this just line, right? And similarly, another students can say, no, sir, I'll take this. This is also true. The beam can also travel this direction. Okay. And then eventually meet some point here. Okay. And then we get the merge here. Let's say P prime. Okay. So one of the students yesterday, he was asking why it will deviate, right? So it is not deviate. As per the Huygens principle that the beam will travel in all direction, we have a ray along that directions. Okay. So so now let me erase it because the picture will be much more complicated and very difficult to explain. Okay, so now we have a beam, a light ray along this direction, which will make an angle theta with respect to on diffracted beam. Now I will call diffracted because the light will have bending kind of structure, nature when it passes across this edge of this obstacle. So now this diffracted beam will make an angle theta with respect to undifracted beam that represented by broken dashed line, and they eventually meet at the over the center of the screen. So now this beam will meet at point P. Why? Because the distance between lens L2 and the screen is at focal distance. So therefore they will definitely converge at the screen. So now we will test. So what would be the intensity at this point on the screen, namely P. Okay, and if you look this schematic diagram, what you'll find there are some variables or parameter. For example, the theta, the angle between diffracted beam and undifracted beam, and then we have B, the width of the slit. Assuming equally spaced point sources over screen, there's n number of equally spaced point sources, again according to Huygens principle, then the distance between any two consecutive point sources will be b over n minus 1. So number of points, so delta will be b over n minus 1. So this capital delta represents the separation or distance between any two consecutive point sources. So look, so this is purely imaginary, right? Because the distance can vary, so therefore it does depend on the number of point sources. Okay, so this n you can have as your, you can consider as your choice. So therefore the spacing will be according, or spacing will depend on the value of small n, the number of point sources over the screen. So now this A1, A2 up to n, as I said, point sources on the slit. Is this clear so far?
Yes, sir.
Yes, sir.
So the diagram part is clear. So what
Yes,
are
sir.
these? And as I said, the notation of symbols that I am using, I have explained here. Yes, a source of monochromatic light, L1 fast lens placed at its focal length from the source S, so that parallel beams of light can be produced. F1 focal distance of L1, MN slit, or you can call operator. L2 second lens used to produce diffraction pattern on the screen. F2 focal distance of L2. AB a screen placed at focal length F2 of lens L2 to observe diffraction pattern. So all these symbols have written down.
Can
Now
you please explain that R equal to CT part?
okay, so these are, is nothing but distance between a source and the fast wavefront, you can say. These are. So this distance will be how much? If we wait for time t, right? And what we'll find that the light will travel at distance ct, where c is the velocity of light. So therefore, the distance r will be ct. Okay, then we can draw the fast wavefront. And similarly, let's say we are looking at time t prime. So then let's say I can say r1 will be ct1, right? So this could eventually represent the radius of this one. You can see this sphere, the r prime. So r prime will be distance that light beam will travel in all direction. If we are considering, they will travel in all directions because this is a point source as per Huygens principle. So how much distance it will cover? The r prime, or you can say r1. So similarly, you can draw again sphere here. Then you can say the r2, which is c22, and so on. So r is basically the distance traveled by beams that comes from the point source. Is it clear?
Yes, sir.
Excuse me, sir.
Hello? Have I clarified your question?
Yes, sir.
Okay. So,
Excuse me, sir.
yes.
So please repeat the distance between two wavefront part.
Sorry, your voice is, breaking. Yeah, tell me.
So distance between two wavefront.
So distance, you can say yes. So distance between two wavefront as well, okay? You can have R, R1, R2, and so on. It purely depends on how you are, taking T or T1, the time. So therefore, we have, distance accordingly. So this is a completely, a very arbitrary variable, okay? It depends on, observer.
Yes, sir.
Okay, so let's move on. So as I said, we have, equally spaced point sources according to Huygens principle. And I have explained these things, right? So, and you can notice the symbols or notation that I have used for schematic diagram. I have mentioned them in great detail here. Okay. And as I said, the theta is the angle between diffracted beam with respect to a set of parallel beam. And so that portion I have, enlarged here. A1 and A2 are two conjugative point sources. Delta is the distance between two these conjugative point sources. And we would like to know what is the diffraction pattern at the point P, which is again arbitrary because theta is arbitrary. And if you look this schematic diagram, what you can conclude immediately that it is easier to calculate the relative path difference between any two conjugative beam rather than calculating the total path difference or total phase difference. And since these are set of parallel beams, so whatever the extra path will travel by the beam A to B to P compared than A1 B1 P, it will be remain same as the extra path travel by A3 B3 P with respect to A2 B2 P. So in general, an extra path traveled by a beam comparison to its conjugative beam will remain same. So if somehow we could find that extra path difference, then we can, by knowing the wave function wave associated with any one of this beam, and by knowing the path difference, we can get easily the wave associated with other beams. So whatever I said, let me show you here, and you will get your doubt will be cleared. So here I have picked two consecutive point source beam named A1 and A2, and this is the extra path traveled by the beam A2 B2 P compared than A1 B1 P. And the extra path is A2 A2 prime, and that extra path delta x which A2 A2 prime will be capital delta sine theta simply from these geometrical configurations, where theta is the deviation of the diffracted beam in comparison with the undiffracted beam. And delta is the distance between any two conjugative point sources. And since this equal is spaced, so therefore this delta will remain same. So the delta phi will be 2 pi over lambda, this path difference delta sine theta. And as I said, let wave associate with the light beam A1 B1 P is A cos omega t, where A is the amplitude of the incoming beam, omega is the frequency of the incoming beam. That means this one. This. Then immediately you can figure out what would be the wave function associated with the A2 B2 P, because the phase difference, which is 2 pi over lambda delta sine theta, you simply add, then you will get the wave associated with the A2 B2 P light beam. And you can repeat this procedure to get wave associated with the rest of light beams that eventually merge or converge at the point P over the screen. Okay, so the wave represents to A to B to beam light beam will be A cosine omega t minus delta t phi. If you like, you can also choose plus delta phi. And if you like, instead of picking A cosine omega t, you can choose sine omega t as well as the combination of this, or you can take the complex waveform. It's up to you. For the simplicity, I choose this one. And if you like, you can also add a phase vector by initializing the phase. Therefore, phase will be 0, and hence the A to P beam light will be A cosine omega t, either plus delta phi or minus delta phi. And similarly, the A3 B3 P light beam, so this one, A3 B3 P, the same path difference, you can draw the perpendicular, again the same path difference in comparison this one. And since you know the A2 B2 P light beam wave, or wave associated A to B to P light beam. Therefore, you can easily construct wave associated with A3 B3 P beam. Omega t minus delta phi, again minus delta phi, 2 delta phi. Similarly, you can get the wave associated with all these light beams. Those eventually converge at the point P over the screen. So this part is clear? Yes or no?
Yes, sir.
Okay, so let's move on.
Yes, sir.
So the resultant wave function, and then we know the principle of superposition. So therefore, the resultant wave function psi at the point P due to superposition of all these diffracted beam, namely A1, B1, P, A2, B2, P, up to N, B, and P light beams is simply this principle. By choosing the equal contributions. So therefore, we have this formula. So now it is a cosine summation series. I put it as an homework and you have to do it. And if you simplify it, then you'll get this mathematical expression. So now instead of delta phi, I rewrote this equation in terms of phi. Okay. It's not because to make the thing simpler, right? So delta phi, I just redefined phi. So now this expression will get. And now this is the resultant wave that converges at the point P. And then we can easily get the intensity from this resultant wave. So with phi equal to over lambda delta sine theta. But if you look this mathematical expression, that you can suddenly realize that you can further simplify this mathematical expression, because the small n, right, which is completely arbitrary, but it does depend on the v, which is the width of the slit, and the theta. So therefore, if you do, and by considering n is very large, then delta will be b over n minus 1. And since n is large, so therefore it can be approximated b over n. Okay. So now n minus 1 to this term, n minus 1 over 2 pi could be approximated n pi over 2 because n is very large. And n over 2 by substituting the value of pi, which is 2 pi over lambda delta sine theta. And what is delta? Again b over n. So now n will get cancelled, we'll have this. So now what we observe, that n minus 1 2 over pi is nothing but it's a constant. It is not constant, but we translate to another variable theta, namely deviation of the diffracted beam with respect to undifracted beam, and we represent it beta. Okay, so now we have sine n pi over 2 and sine phi 2, and pi over 2 will be what? Pi over 2 will be 2 beta over n, simply from this mathematical expression. N pi over 2 is beta, so therefore pi over 2 will be 2 beta over n. And when n goes to infinite, when n is very large, what happens? The sine pi over 2 could be approximated by pi by 2. So everybody knows the expansion of sine theta, which is theta minus theta q over 3 factorial theta fifth over 5 factorial. I guess this is correct, right? And when n is very large, then phi goes to 0. When n is very large, then phi goes to 0. So therefore, for small phi values, that can be approximate to first. So this will be vanishes. So therefore, sine pi over 2 is beta over n. And n pi over 2 is nothing but beta. So this resultant wave function will be a sine beta or beta cosine omega t minus beta. That I have written down here. So is this clear to everybody? Am I audible, first of all?
Yes, sir. Sir, does beta have any physical significance?
The beta is another way. You can see, right? The pi is a constant, lambda is the wavelength of the monochromatic light, v is the slit width, and theta again it's a variable, right? It is the deviation of the diffracted beam with respect to undifracted beam, right? This theta.
Sir,
So
beta.
beta that in the significance is in the sense it explains how much the diffracted beam deviated compared than the undifracted beam here. And it is in fact a variable, right? If you look, so it is an arbitrary point P. So do remember I said it's an arbitrary point P. So therefore theta is a variable. So beta will explain how much this beam get diffracted or bent with respect to undifracted beam. So this is the physical significance of beta. And we'll also see later on, okay?
Okay, sir. Thank you.
So now we can rewrite in terms of this. And now again it is in a wave function form, which is cosine omega t minus beta. So therefore what we can find, so these are the values that I have defined, okay? You can read it out. So I can write that I can see that the amplitude, so this stands for the amplitude part, because this is the wave function part, time is here, but this is amplitude part. And what we found that the intensity of the superpositive at the point P, which is directly proportional to amplitude part, is sine beta over beta square. A square is the amplitude, I naught, intensity of the incoming wave, and this is the correction over this intensity I naught due to diffraction. So now what we got, that the intensity of the diffracted beam that made at point P on the screen, which is I naught sine square beta over beta square. As I said, theta is the deviation of the diffracted beam with respect to the undifracted beam. Therefore, beta will take care whether this intensity will be maximum, minimum, or any value between minimum and maximum. And therefore, by maximizing this intensity with respect to beta or theta, will give you either minimum and maximum condition. Okay, so let's do that. So how we can find the position of maximum over screen. So as I said, the for minimum condition, intensity will be 0. And equation 5, and it could be 0 when sine square beta over beta square equal to 0. Okay, because if we make I naught equal to 0, then it is meaningless, because I naught 0 means there is no incoming wave. So, and therefore sine square beta over beta square equal to 0. And this immediately implies sine beta equal to 0, provided beta not equal to 0. Why? If beta equal to 0, then it will be sine beta over beta will be 1, right? 0 over 0 form. And this leads to I equal to I naught, which is maximum intensity. So what we learn that when beta equal to 0, which is pi b sine theta over lambda equal to 0, this implies when sine theta equal to 0, so that leads to what? That maximum intensity. When theta sine theta equal to 0, that again it leads to theta equal to plus minus n pi, right? Provided n equal to 0, 1, 2, and you can see that when theta equal to 0, that means the set of undifracted beam, they will lead to the maximum intensity. Hence, what we observe at center of the screen, this leads to theta equal to 0, where the intensity will be maximum. I naught. Is it clear to everybody?
Yes, sir.
Okay. So at center of the screen, the intensity is maximum. So coming back to this mathematical expression, which will help us to find out the bunch of minima, and that leads to beta equal to plus minus n pi, provided beta is not equal to 0. But here theta equal to plus minus n pi leads to maxima. So this is condition for minima. When beta equal to plus minus n pi, that means sine theta equal to plus minus n pi, then this is the condition for minima. And for maxima, what we have to do? We will, optimize this function 0. And then this will give either maximum or minimum. Since we know the condition for minimum, if we throw out the minimum, the set of minimum points, the rest points will give you the maximum. So that's exactly I have done here. So if you do the first derivative and equate to 0, that will we'll find this expression. But as we know, okay, if you look this mathematical expression, this will be 0 when sine beta equal to 0 or the term sitting in this bracket is 0. Sine beta cannot be 0 because this is the condition for the minimum we have already seen. So in order to maximum, so beta cos beta minus sin beta must be 0. And that leads to tan beta equal to beta. So we got an expression which says the variable is a function of itself. And how to solve it? So this type of equation in mathematical language, in mathematics, called transcendental equation. And the only way to solve it through graphical methods. Okay, if you don't want to use computer. So graphical method, what does it say? That we draw these two functions, tan beta and beta, as I have drawn here. So these red lines are tan beta, and these solid lines that passes through the center is the y equal to beta. This is y equal to tan beta, and tan beta equal to beta will satisfy the point of intersection between this tan beta function and y equal to beta function that I have marked over here. So what we found that when beta equal to 0, that condition satisfy, and then when beta is almost equal to plus minus 3 pi over 2, similarly plus minus 5 over 2 beta condition satisfy. So we got the solution through this graphical approach. Okay. So what we have already seen, when beta equal to 0, that leads to maximum, and it is indeed at the center of the screen, and this is known as principal maximum, which occurs center of the screen. And other conditions, which is beta plus minus n plus half pi n equal to 1, 2, 3, this is condition for other maximum rather than principal maximum. Okay, so now we found the condition for minimum and maximum, and that will help to locate the minimum and maximum over the screen. And as I said, that it can be also translated in terms of theta, that I have written down here, the minimum and maximum condition in terms of theta. Okay. So is this clear, everyone?
Yes, sir.
Okay. So now, so let's try to plot it, okay, over the screen. So this horizontal line represents the screen, and O is the center of the screen. And by using this, I equal to I naught sine square beta beta square, which is the intensity distribution over the screen due to superposed of the diffracted beams. When theta equal to 0, this is to I equal to I naught principal maximum, and then what else? Other maximum. Beta equal to plus minus 3 pi over 2, beta equal to 5 pi over 2. And if you substitute, you will get I naught over 22, I naught over 62. That I have represented. That means the first, you can say this is principal maxima. So then you can say the first, you can say the secondary maxima, which are intensity I naught over 22, and the third and then third maxima will have intensity I naught over 62. Okay, and 3 lambda over 2 beta, these are the position of minima. Again, we'll get from this condition sine theta equal to plus minus n. So this is the distribution of the intensity of the superposed wave around this, the center of the screen. Okay, and so now you can see how the intensity fluctuates. So it means if you move away from the center of the screen, okay, so you will observe the fluctuation of the intensity, right? Which intensity decreases as you move away from the center. So that's the definition of the diffraction. If you remember yesterday at the very beginning, we talked about that the intensity will fluctuate as you move away from the center of the, you can see the point. So now this is the final diagram which explains how the intensity pattern distributed here. Okay, so we have central maxima or principal maxima, which has high intensity, and the intensity decreases as you move away. And as you can see, so this is the geometrical shadow region. It has been extended towards geometrical shadowy region, and similarly in this way. It's as if the light has been spreaded, across the geometrical shadow region. So this is all about theory behind diffraction, and we indeed studied this diffraction theory using a single slit experimental setup. So any quick question? Hello? Hello? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, any questions? Give me for a moment, I'll come in there. Yes, any questions on today's lecture? Hello? Am I audible?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay, by the way, so the recorded lecture as well as lectures, today's lecture note, I'll upload both. So you please go through them, and you can get your doubt cleared if you have any doubts. Okay, and tomorrow I might not conduct any class. Okay, so if that is the case, then I'll let you know over WhatsApp. Okay, so and we'll meet next week to discuss about another important phenomenon produced by light, namely polarization. Okay, so thank you everyone. We'll meet next week. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.